All right. Hi, everyone. So I'm here to talk to you about Linux rootkits. I'm Darren. I do security research and Linux stuff. All right, so I'm just going to get straight into it because I have a shitload of stuff to cover and half an hour. So I'll open up with, so what I'm talking about here is LD preload-based Linux Userland rootkits. So I guess the first thing I'll cover is what is LD preload, and LD preload is an environmental variable interpreted by the dynamic linker, and it allows you to put libraries in ahead of other libraries. So for the people who are more familiar with Windows, it allows you to change the search order of how libraries and code are loaded into software, so you can put stuff in ahead of other stuff. So it's really useful for debugging. You can change execution behavior at runtime, you can replace functions, you can substitute out functions, you can hook and stuff. And of course, that makes it really useful for rootkits. It can be set globally, system-wide on Linux with the etcld.so.preload file, which is, it's just a file and it parses it really loosely. So like the dynamic linker will look at this file and anything that looks like a library it will try load, which is quite fun. On OS X, there's an equivalent called dild insert libraries. On Windows, we've appinit DLLs, but if you mess about with appinit DLLs on Windows, just nothing works. It's pretty much documented as here be dragons. If you go here, you're on your own. Pretty much any platform has some way to override the library search path, which is great because it means you can write super portable rootkits. So we can replace functions at runtime. We can mess about with what programs are doing. So we can make programs lie. So right, rootkits. And this allows us to hide stuff, do stuff in the background, blah, blah, blah. So I kind of come up with a list of like, because everyone, when people think rootkits, people are like, oh, kernel rootkits, kernel modules and, ring zero stuff. It's like, no. The problem with writing kernel rootkits for Linux is it's a pain in the ass because the Linux kernel ABI is not considered stable. They keep changing shit all the time. So like you end up having this like big file of if-defs or having to recompile your kernel rootkit for like every single major release of Linux, which is a pain in the butt. So instead, you just write one userland thing which works everywhere. And like the pros are like they're stable, they're easy to write. It takes like 20 minutes to implement a new hook. The cons are like that they suck. They absolutely suck because there is one place on disk where they live. So if you're a forensicator, you just cat etc ld.so.preload and you've probably found the kit. And they also mess up performance, which I'm going to point out later. So I'm going to talk you through first how to write one of these for those following along who want to have a bit of fun with this. So what you do is you just identify something you need to hook. So if you want to hide a file, you just strace ls and you see what function calls ls looks at and does. And then you go, okay, what of these do I have to mess about with to hide stuff? You figure out how to hide the stuff, which is usually just like do a string comparison. If it's got like a magic string in it, hide it. And then you write the hook or, draw the fucking owl. I believe it's termed in and then you just repeat until, the thing works. So I'm just going to go through a few examples. So this is a very simple hook that cripples the randomness function on Linux. It'll just return 42. So we've a simple program that just calls rand and gets a number, but when the hook is installed, it'll only ever return 42. And this kind of, it's kind of like the hello world of writing these hooks, because 3 lines. But it shows you you can break the randomness in video games or break the randomness for generating cryptographic keys by corrupting the random function. You can also do conditionals in your hooks. So if we go back, that hook's it's just return number. It's not very sophisticated, but we can add we can have it load the actual random function and have a getenv. So if a certain environmental variable is set, actually return real randomness, otherwise return broken rand. And this is just an example of that where if we set the hex equals lol or hex equals whatever and load it, it won't do the thing. It's this conditional will come in handy later. This is just the very contrived, very simple example that I can use to show you how these hooks are written that actually fits on a slide. You can add multiple conditions. You can do stuff basically your hooks act as IO filters. So here we have a reader example. It's an actual practical example that's partially borrowed from the Jinx 2 rootkit. So all you're doing is you're creating readdir, and then you're creating the original readdir, and if string your hidden file name, if the responsive readdir contains your hidden file name, return buggery nothing, return like nothing. However, if the directory being LS'd doesn't have your hidden file, then you can just return the file contents so the admin doesn't, just have all empty folders everywhere. And this is just an example of this working. Like, you run ls and you've got like the hide me's, you do the preload and run ls, and the hidden files are hidden. And this is actually a great time to show one of the timing attacks I found that allows you to detect these rootkits, because one of the interesting things is, because you're doing all that string comparison crap in the middle of your rootkit, you absolutely murder performance. So, like, every time readdir is called, performance, like, takes a hit because you have to do all this diversion and, like, go off, like, to check string comparisons, which is computationally actually quite expensive. So, because of all that extra stuff, we can actually demonstrate, like, the actual performance impact. So, with the hook installed, you've got, like, the real time is, like, 3 milliseconds, whatever that value is, like 0.003. Without the hook, it's 0.002. That's like a 50% in worsening of performance. And that's just like one pretty contrived simple example. If you imagine that system-wide, every time readdir is called, or any other hooked function is called, you're getting whacked with like a 50% plus performance hit. Somebody's going to notice, It's like, okay, you might be able to find all the hidden files and stuff, but your computer is slow as fuck. Your computer doesn't work anymore. It's like the whole thing, virus is slowing down my computer, but actually real. So another thing you can do with these is you can, like, it's really trivial to implement local backdoors with preload kits, and they all, like, all the rootkits I've examined in the wild that use LD preload pretty much all implement the exact same local backdoor, and it's just, if an environmental variable is set and a setuid binary is being ran, spawn a root shell. They all do it in exactly the same way, and it's kind of funny because, like, you just have this one function that's just been copy and pasted across every single rootkit in the wild, and this is exactly that function. They're all just variations of this, where it's like, oh, if an envar is set and the current EUID is 0, like if you're running like sudo or something, drop a root shell instead. And then what they do is they put a call to this hook in every other hook, so it makes sure it gets called. So, like, you just shove it like in the middle of the access hook where it's not going to do any harm. Or you could stick in a constructor or destructor, but this is how it's like done in practice. And this is how that backdoor works. You, on the system's got this rootkit installed, you set the magic environmental variable to whatever value and run a setuid binary. Next thing pops a root shell instead of, like, doing whatever it's supposed to do. It's, like, pretty straightforward. But the thing is, all these rootkits also implement, like, a wide variety of remote backdoors. And this is where it gets quite interesting. So this is where it gets neat, and I'm going to have to go back and forth a bit. So most of them, the Jinx 2 family lineage of these rootkits pretty much all hook the accept function. And the accept function is like what's called, like, when a socket connection is made to, like, when you connect to something, like when you are listening on a socket and then you accept the socket, blah, blah, they all basically just have like a magic port that, like, if a certain magic port is, like, set, then it drops you a shell instead of giving you, like, access to the web server. A bunch of others like Umbreon, Father, Vlani, and a few other of the slightly later generation rootkits, hijack PAM. They add, like, an extra check to PAM to implement, like, a magic password in SSH. That's pretty popular in some of the stuff in the wild ones. And then another example one I saw hooks right, where if you try log in with a magic username to SSH, it triggers, like, a hook that spawns, like, a bind shell on a high port. And it's, like, just kind of weird. And then some of the earlier ones use, like, port knocking, magic packets for their more remote backdoors. Like, if you send a packet with a certain, like, magic value in it, it would send back a reverse shell. Some of the more recent ones I've seen have done stuff like hot swapping etc password and etc shadow at runtime. So, like, they will intercept, like, the call to, like, read etc past WD and give it, like, a replacement past WD file in memory, which I thought was quite neat, to, like, implement, like, an extra user. And some of them do that with the authorized keys file. Basically, there's infinite potential to come up with like weird new ways to like implement remote backdoors entirely in user space by hooking various functions. You just have to kind of think outside the box a bit. These are just the ones that we've actually seen implemented by people and actually used. So like, I'll go through the example of like how the accept hook works, and it's pretty straightforward. So this is from Jinx 2, and all it is you're replacing the accept function with your own accept function, and you just get, you do accept on the socket by getting your old accept function, and then you call the drop dupe shell with the socket file descriptor and the address. And what happens in that function is actually really simple. It just checks if the source port of the connection is between a high and a low number, and if the source port's in that magic range, instead of like serving up Apache 2 content or like an SSH login or whatever, it serves you up a root shell. And it's like really straightforward, and it's like really kind of elegant and simple, and also absolutely murders the performance of all your network daemons. Like your web server's performance is now absolutely just no. It's just slow. It's messes things up pretty badly. Like your web server perf will drop, your database perf will just go through the floor. And this is like an example of like what to the user of the rootkit, what it looks like. So if you connect to a victim, like from any random port, you get the SSH banner, right? But if you set the magic source port and you're connecting specifically with the source port of 31337, the destination port of whatever service is open, it'll instead prompt you with a password for the backdoor shell, and then, you get your shell. So that's the most popular because Jinx implemented the accept hook, and then everyone just copy and pasted that into their own rootkits because that's how malware is written. It's just Control-C, Control-V, apparently. Everyone's lazy. So the other kind of main one we see is the backdooring PAM, which is really neat. So PAM is the pluggable authentication module. It's like how authentication is handled in most Linux. So what the rootkit named Father does is quite neat. It replaced the PAM authenticate function, and it just checks like if there's a magic secret password has been entered. It just does a quick comparison, and like if secret password, then you also get logged in as any user, which is pretty neat. If the magic password is not provided, it'll actually check for a real password so you don't disrupt normal users trying to log in. Now, the one problem with the PAM backdoors is that they're really easy to scan for, and I'll get to that later. You can detect them remotely if you know what you're looking for. But we'll get to that later, because with remote backdoors like the accept backdoor, when they break, they really break. Like when your backdoor stops working, it really stops working in a really funny way. So I thought to myself, I'll try find like broken rootkit installs on the internet, like live infected boxes where like something's gone catastrophically wrong. And I was able to find a load of them. Like I found a copy of a rootkit called libmdma, and it turns out it was one of the first ones ever written using the LD preload technique. And I found that just by I found an IRC chat log of somebody complaining their system was banjaxed, and I just started Googling for the file name they mentioned, and then found it on some random web server, and clearly the rootkit bit had broken because it had stopped hiding itself, and it was now just serving itself up as a file. So I was able to get a sample, reverse it, wrote a lengthy piece about it. But I decided to look for other rootkits that have gone wrong. So I found that the dynamic linker on Linux spits out a very specific error message when it's trying to preload a library, but the library is broken, it's the wrong architecture or whatever, or it's just missing. So I put that string into Showdown, just kind of thinking this is not going to find anything. This is dumb, but no, it turns out it did find tons of stuff. So you get this error message, object blah from etc LD cannot be preloaded, but you get that message everywhere. Every single network service on these TerraMaster NASes was spitting out this error message, and I was okay. So what the story with these are network NASes, and somebody had gone around, somebody had compiled some rootkit and tried to install it on like thousands of NASes, but they compiled it for the wrong architecture because they were idiot. They compiled it like for x86 64 and tried to install it in a bunch of ARM systems, and I'm like, script kiddies, man, you know? Couldn't even, you know, they don't even check, so they just hosed all these things, but like they left a copy of the rootkit just sitting around, you know, like on all of these. And it was pretty funny because when I started Googling, I found like people have been complaining about like their NASes were broken because the skids had like put this broken rootkit on them. So people were like posting on the TerraMaster forums going like, hey, I'm getting this weird error. And like the TerraMaster people were just like, just delete the file. Nothing is wrong. You know, completely ignoring the fact, like completely like denying and like trying to steer their customers away from like, you have been wrecked because our software sucks. But, you know, I thought it was an interesting aside, like, that because these guys had, like, compiled their rootkit wrong, like, they had very publicly messed up in a way where, like, you could actually see. So I started digging into this one a bit more because I thought it was interesting, you know, because, like, the vendor's like, just delete the file. It's fine. Everything's fine. You know, it's just a software bug. It's not like you've been owned, you know. So I also found like reference on like random Chinese forums to like, hey, I'm getting this weird error. Here's how to fix it. And like, I was like, okay, so this is clearly like somebody has clearly tried to use this libsystem.so rootkit in the wild quite, you know, quite, what would be the word? Generously, I guess. They've spread the love around a bit. So it turns out that it was the Kinsing group. And the specific rootkit they were using was a modified version of one called Bjork, which is open source. And it just didn't work on some hosts because they compiled it for the wrong architecture because they're complete idiots. And they were using it to like hide badly a crypto mining campaign. And they were spraying around like Log4j to drop this rootkit. And, you know, script kiddies. Like really low grade, absolute bottom of the class tier cyber crooks. 0 out of 10, you know, they get absolutely no points. No style points either, you know, like copy and pasting stuff and then somehow still screwing up. So after this, I started trying to think like for if you come across one of these samples, it can be a bit of a pain. Like you've got like a shared object file that's your rootkit. Like how do you categorize it? Like for the blue team guys, like, what do you do? Like, how do you categorize it? How do you bucket it and cluster these samples? And I started trying to come up with like some kind of way, and it's an Excel. Spoiler, it ended up being an Excel spreadsheet in the end because that's apparently how everything's done. But I started coming up with like a worksheet for analysts, and I'm still working on this, and I'm probably going to upload the thing in the next couple of weeks to GitHub or something. Like a worksheet for like your incident responder to go through when they encounter one of these rootkits, and like, here are the steps to like identify it, mitigate it, and then work out how to detect on the rest of your network. And it's quite straightforward. Like the first one would be like just open it up in IDA or Ghidra or Radare or whatever your favorite reverse engineering framework is, and just identify what functions it hooks. Because you can often like figure out which one it is just based on the unique subset of what functions it actually implements a hook for. The second thing you need to do in like your worksheet of identifying these things is, has it just copy and pasted code from other rootkits? And the answer is probably yes, because they all copy and paste code from Jinx 2 because it was like the first one that actually worked. So like the diversity of code out there for these things is pretty small. Then the next, like, you can then figure out like what remote access method does it implement? Like, does it implement a PAM backdoor? Does it implement an accept hook? Does it implement like port knocking? And this is very useful for like remediation for scanning your network for it later on. Does it implement self-protection methods? Like when you think you've uninstalled it, has it actually sneakily reinstalled itself while you weren't looking? So a few of them, I think it's the Umbreon one. When you try delete it, it hides itself in memory, lets you delete it, and then by hooking the destructor of ORM, like when ORM is, like when after ORM has ORM'd a file, before ORM's process terminates, it then like reinstalls itself. Like it specifically hooks like the delete, like the RM binary, in a way that like allows it to reinstall itself after it's been deleted, which I think is hilarious. Because you're like, yes, I have fixed it. The problem has been remediated. And it's like, actually, no, I am still here. Another thing to look at, you can fingerprint them pretty uniquely by like, how do they obfuscate strings? Most of them don't, but some of them use like really, really terrible XORing of strings that just like, you know, you can figure out the key to pretty quickly. And then very, very few of them, a limited subset of them, actually encrypt strings in a way that's meaningful and a pain in the ass to reverse engineer. The other thing that's important to figure out with a sample this is, how does it decide what stuff to hide? Like, is it magic string based? Is it magic group ID based? Is it extended attributes based? And like, once you figure out these things, and once you've gone through all those steps, you have probably identified which exact piece of nasty you're dealing with. And of course, it'll all end up in a giant Excel spreadsheet. Like the what functions does it hook one is something that I've got a giant Excel spreadsheet that I need to publish for this, but like I basically picked a bunch of example rootkits that I'd source code for and dumped out every single hook they implemented into like, on one side of the spreadsheet, you've like a list of every single possible hook, and then the names across the top and a little tick box. So when you get your sample, you go and you cross-reference it, and you can pretty accurately identify with no further reverse engineering or hard work what rootkit you're looking at just by cross-referencing it against a spreadsheet. It was a pain in the ass to do this because like the Vlaney rootkit seems to implement like a couple of hundred different hooks, because whoever was writing it was like clearly like, I'm going to hook that function and that function and that function. Oh, more functions, just going to backdoor all of them. So to like documenting that took about a week. Using like just by looking at code reuse. One thing that I think would be interesting to look into is writing like flirt signatures or Yara rules to automatically detect like code reuse from like snippets that have been stolen and repurposed. I actually found out that's how a company called iNetzer, I've no relationship with them, but they have a weird product for malware stuff called Code DNA, which it turns out already implements this. And they say it's super effective, and it seems pretty effective at like reducing my workload. Like if, just instead of having to reverse engineer the function, just check, have I already, is this present anywhere else? Identifying what backdoor methods it implements is important, because if it's got an accept hook using SSL, you're looking at a Jinx variant every single time. If it's doing a PAM backdoor, it's going to be magic password based every single time. They're all very similar. They're all copy and pasted from the same code. So this is where it gets neat, because if you actually take apart the remote access bit, you can do network scanning. So like if it's the accept hook, you just figure out the source port that the sample's looking for, get mass scan, set -G source port number, and scan your network, and then diff the output against a scan with randomized source ports. And if you see something weird, it's probably one of these, because you'll get a differential response. For PAM backdoors, if you can like figure out the magic login, just sweep your network for it. Same for port knocking ones, just replay the knock sequence across your network, and if you start getting connectbacks, you've got something is very, very wrong. The self-protection methods, usually constructor-destructor hooks. Very few of them implement working self-protection. Most of them just rely on like stealth. The ones that do reinstall themselves, though, are very funny because they're a real pain to remove. You have to like reboot from a live disk and, actually delete the thing. String obfuscation, most script kiddies are too lazy to bother, but like some of the samples like Azazel actually implement XOR stuff and some other stuff. Automating deobfuscation of these will reduce your workload, and there are IDA Python scripts and stuff for that. The marking files to hide, again, blah, blah. Already covered this. So yeah, this is the bit that like where it's going. So like we've seen where it is, but where it's going is kind of neat. So like most of them are general purpose, like remote access and hiding. But some of them we've started seeing like much cooler, limited scope, specialized ones lately. So I'm going to talk about a sample called libcurl. So it was trying to hide by calling itself libcurl. So this rootkit was dropped as part of a crypto miner campaign. It was discovered by a crowd called Sandfly Security, and they claimed that it was capable of evading a bunch of Linux EDR products. When I took it apart, it didn't have any magic that would it didn't have any special sauce or anything, so I guess just Linux EDR products suck. I guess that's the case. But this one was neat because its one job was to hide a crypto miner. And all libcurl did was it hid the miner's processing files, but also hooked the functions to check CPU usage. So it would lie and it'd be like, oh, the load average is really low and there's not much CPU usage going on, while your CPU is turning into a space heater in the background. Sysadmin's logged in oh, no, load is really low, everything's fine. But yeah, this, somebody had written this specifically to, hide their mining, which I thought was really neat. Except for the fact that, if, it's a physical server you're near, you're going to hear the fans going and you're going to be like, something's up. But they put a lot of time and effort into, finding a way to coerce, HTOP and PS and stuff into reporting the wrong, load averages. Which I thought was kind of neat, because somebody had, they'd actually put effort in. They put a bit of work into doing their crime. And the last one that I want to point out, and this is just kind of where things are going, that's kind of interesting, but it's completely irrelevant because nobody can afford GPUs. But a few years ago, some guys figured out that some Team Jellyfish, they worked out, they could use the LD preload thing and then load their code into the GPU, their whole trick was hiding executable code in the graphics card's memory by loading in some OpenCL stuff. It's open source, their work. It's really, really neat, and malware hiding in your graphics card is kind of neat because nobody writes antivirus for graphics cards. But also, nobody can afford graphics cards because they cost, you have to remortgage your house for them. That might become relevant in the future if, we find a way to get graphics cards cheaper again, but no point. But, I can see that, that kind of stuff, hiding in weird bits of your system, being potentially where things go. And these are just references, and more references. And there will be yet more references on GitHub and stuff when I upload the slides and all the supporting material. The GitHub's just my github.com/my name. Yes, I guess any questions? Yep. Yeah.
Sorry. Have you done any research on, say, containerization? Does that help in any way?
So I didn't get to cover that here, but I have seen some kits that are specific to containerized environments or environments using containers. I came across one that has a function that allows it to create a hidden LXC container and hides an entire container from the admin, which I thought was really neat. And I've seen others that try to abuse Docker a bit, but they kind of don't really work yet. So I guess some stuff, I think we're going to see more of this in container environments though. It'll be neat to see how they impact the performance of your container environment, because I imagine because the performance impact that they have, they'll probably trash your Kubernetes setup by just making it slow.
For your Shodan search, what was the search string? What's the Google Doc to find the broken rootkits?
Let's go back. It was just the error message. ld.so.preload cannot be preloaded, cannot open shared object file. You just stick that into Shodan and you'll find so many systems that could have been backdoored, but the rootkit didn't work because somebody was incompetent.
Did you test for Did you test for a Windows subsystem for Linux?
Not yet. I haven't played with that very much yet, to be honest. I only recently came into possession of a computer running Windows. I'm still not sure how it works. It's kind of weird, you go from like 7 to 10 and you're like, uh-oh, they've moved everything. Guys, I'm scared. But I actually do intend to test some of these on, because I do think they will work in WSL, because WSL is just Linux in a container now. It's a VM now?
WSL 2 is for Hyper-V. Along with the
Ah.
The networking will break ever so slightly, the processing sharing will break ever so slightly. They'll get you 99% of the way there and then drop you off a cliff.
So we're nearly in the year of Linux on the desktop.
Yeah. They're shipping with X.
Okay.
WSL 2 ships with X.
So graphic stuff works. Okay, I'll actually have to power on the Windows machine then and actually maybe use it, because then I can actually edit PowerPoints properly. All right, that is that. If anybody has any other questions, you can grab me later.